So today we're going to be looking at nuclear fusion. Now on Earth we have been unable to successfully produce some sort of mechanism where nuclear fusion can occur. So we need to go and look at the sun. Now at the beginning of the sun's lifetime, our sun was mainly, let's just say 99% of hydrogen, or you could say protons. But as the sun has evolved until what it is now, nowadays the sun is probably only 49% of hydrogen and around 50% of it is helium. And nuclear fusion is the reason why there's been this change. So let's look at two protons. We know that at distance greater than 0.5 femtometers, let's just say in this case it's 1.5 femtometers, we know that there will always be a repulsive electrostatic force. But at a slightly larger distance, we know that the strong force will act to attract them together. However, at smaller distances, smaller than 0.5 femtometers, we know that there is as always, an electrostatic force of repulsion. So this electrostatic force would act away from either proton. Also, the strong force would act as a repulsive force as well. So in a typical scenario, we cannot get these protons to meet each other. However, the sun is special because the core temperature of the sun is roughly 10 to the 5 Kelvin. And because there is such a great temperature, there is therefore a lot of kinetic energy that these protons will have. Therefore, due to a high kinetic energy, these protons can overcome the force of repulsion. So what that means in the sun is that these protons can fuse together. So in the sun, what you're basically getting is hydrogen fusing together to form helium. And that's what nuclear fusion is. It's smaller nuclei fuses to form larger nucleus. So let's look at the exact scenario of what exactly goes on in the sun. We will have protons in the form of hydrogen, and these will actually fuse with a neutron to form a heavier version of hydrogen with one proton and one neutron. And in doing so, it will actually release energy, and this energy will be in the form of a photon. Now, I will come to where this energy actually comes from in a minute, but let's still carry out the process of what goes on in the sun. Now, this heavier version of hydrogen will then fuse with another neutron to form an even heavier version of hydrogen, and again, some energy will also be released. And what goes on is this process actually happens twice, such that you get two versions of this hydrogen. And this variation of hydrogen is known as tritium. And these will fuse together to form helium, and you will get back two of your neutrons. And once again, it will also release some energy. So the overall reaction is basically two of these hydrogens plus two of these neutrons, and these hydrogens are in the form of protons, and these will form a helium nucleus. There'll be some amount of energy that is released. But where exactly does this energy come from? Actually, there is a small change in the mass between the reactants and the products. This small change is known as a mass defect. Now, from the equation here, it looks like the helium has the same mass as the two hydrogens and the two neutrons. If you look at the exact values, there is a bit of variation. The helium nucleus is actually a bit lighter, or has a slightly lower mass than the combined mass of two individual protons and 2 individual neutrons. Because of this mass defect, we know that E is equal to mc squared. So therefore energy is released in the form of a photon. So our mass defect, or this delta M, is equal to the mass of your reactants minus the mass of your products. It's this delta M that is going into your E equals mc squared equation. So let's look at the scenario where we're forming a helium nucleus from 2 protons and 2 neutrons. Now, forming this nucleus from its constituent nucleons releases some energy, and this energy is known as your binding energy. So the binding energy for nuclear fusion is the energy released when forming a nucleus from its constituent nucleons. Now, because we're looking at nuclei and nucleons, these all have a very, very small mass. So we've come up with a different mass unit called the U. So 1 U has a value of roughly 1.66 times 10 to the minus 27 kilograms. And this U here is your atomic mass unit. Now, because E is equal to mc squared, the energy that is formed from one atomic mass unit is equal to 1.661 times 10 to the minus 27 times the speed of light, which is 3 times 10 to the 8 squared. That's equal to roughly 1.49 times 10 to the minus 10 joules. And if we were to convert this to electron volts, this would be given as 9.31 times 10 to the 8 electron volt, which is the same as 931 mega electron volts. So 1 U has a mass of 1.661 times 10 to the minus 27 kilograms, and that is a conversion that will be given to you. 1 U produces an energy of 931 mega electron volts.
Now, the best piece of advice I can give you after watching that video is to go off and practice on past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously, go and do all the YouTube stuff of liking, subscribing, and if you found this video helpful, feel free to go and watch any of my other ones.